Very good morning. Today we're going to design a Butterworth analog filter. The problem is like this: design a Butterworth analog high pass filter to meet the following specification. Those specifications are like this: maximum passband attenuation, which is 2 dB, passband edge frequency, that is corresponding to passband attenuation, is 200 radians per second. Third specification is stop band attenuation, which is 20 dB, and the fourth specification is stop band edge frequency, which is 100 radians per second. So if you could recollect this, so this is the typical magnitude frequency response in case of high pass filter, and the specifications that what you are supposed to remember in case of high pass filters are Kp, Ks along y-axis and omega s dash, omega u along x-axis. The same specifications they have given in the problem. I will go through the problem. That is, they have given maximum passband attenuation, which is nothing but Kp, this one. This value is how much? It is 2 dB. Remember, I told you, even though they don't give you the value in terms of minus sign, you should treat it as minus only, because y-axis represents minus 20 log magnitude h of j omega. Obviously, you will get negative term. So Kp is equal to minus 2 dB, and the second specification is passband edge frequency, that is corresponding to this attenuation. We'll have one more frequency, see here, which is omega u, which is upper cutoff frequency. What is the value of it? Its value is 200 radians per second, that is omega u value is 200 radians per second. So along with that, we have two more specifications. One is Ks, other one is omega s dash. So what is the value of omega s? That is, omega s stands for, Ks stands for stop band attenuation. So the value is 20 dB. Remember, again, even though they don't give you the value in terms of negative, treat it as negative. So Ks value is minus 20 dB, and stop band edge frequency, that is corresponding to stop band gain, you have stop band edge frequency. In general, for high pass filter, it is denoted as omega s dash, which is equal to 100 radians per second as per the question. Now, as you know, if you can recollect, maybe in the last problem also, that is when we designed low pass filter, Butterworth only, I told you we know formulas only to design normalized low pass filter. What do you mean by normalized low pass filter? Normalized low pass filter is one in which omega p is equal to 1 radians per second, right? So we know formulas only to design this. Now we'll check what values they have given, or what specifications they have given corresponding to this normalized low pass filter. Have they given you the value of Kp? Yes, of course they have given the value of Kp in the problem. Have they given you the value of Ks? Yes, of course they have given. Since omega p by default it is 1, because we need to consider normalized in order to design a Butterworth filter. So no need to worry about omega p, but check the value of omega s. Have they given you the value of omega s? No. I told you when I explained this particular analog to analog transformation, that is, suppose sometimes they will give you this, we may need to find out this, right? Could you able to recollect these words? Then right now, have they given you the specifications? Yeah, of course they have given you the specifications. And do we know this specification? Omega s, we don't know, right? But there is some formula wherein if they gave you this specification, we can get back this, right? How? It is through this backward difference equation, right? That is, omega s is given by omega u divided by omega s dash. Have they given you the values of omega u and omega s? Of course, they have given you the value of omega u as well as omega s dash. See here, they have given you the value of omega u as well as omega s dash. So I'll use this particular backward difference equation to convert these values which was given into this, because remember this, I know formulas only for designing normalized low pass Butterworth filter. As a result, I need the values that are present here, right? That's why I'll make use of this backward difference equation to convert these specifications to this. Hope you understood the importance of backward difference equation now. So uh, I'll use the same equation. Now look here, normalized low pass filter is given by this in general. So Kp Ks omega p is equal to omega c is equal to 1 radians per second, and omega s, this value I don't know, I need to calculate. How to calculate? Omega s is given by omega u by omega s dash. What is the formula for, sorry, value for omega u? It is 200. What is the value of omega s dash? It is 100. So it is 200 by 100 radians per second. How much you'll get? You'll get 2 radians per second. That will become a values for omega s. Now, do I know the formulas to design this? Yes, I know. Which filter is this? This is low pass filter. Remember this. Right now what I'm doing, I'm designing a normalized low pass filter only. But what is the thing I need to do? What is the thing I need to design? I need to design high pass filter. How I can achieve this? By using something like this, right? By using suitable transformation, I can convert normalized low pass filter into desired filter. Sorry following what I'm saying. Now we will proceed. Now once you know these values, that is the values of Kp, Ks, omega p as well as omega s, can I find out order of a filter? Yes, of course. That's what is needed to find out order of filter, right? That is the values of Kp, Ks, omega p as well as omega s. Now if you recollect the formula, that is n is given by, that is n here is order of filter is given by log of 10 power minus Kp by 10 minus 1 whole divided by 10 power minus Ks by 10 minus 1. The entire thing has to be divided by 2 log omega p by omega s. Now substitute the value and calculate the value of n. See here, minus of minus 2 by 10 minus 1 whole divided by 10 power minus of minus 20 divided by, sorry, 10 minus 1 whole divided by 2 log omega p, 1 by 2. Are you getting 3.7? Yes, of course you are getting 3.7. And you know that it has to be treated as next highest integer. Are you getting 4? Yes, of course. It has to be 4. Once you find out the order of filter, can I easily find out poles? Yes, of course I can easily find out poles. How many poles we will get in general? In general, we'll get 8 poles, out of which 4 are left half and 4 are present in right half. So which poles I need to consider? I need to consider only left half poles. What is the reason behind it? The reason is I am designing stable filter. If you want to design a stable filter, then we should consider those poles which are situated in left half. So in general, what is the formula for finding out poles? It is given by sk is equal to e power j into theta k, where theta k is given by pi by n into k plus pi by 2n plus pi by 2, where k varies from where to where? 0 to 2n minus 1. So 0 here is 0 till 2n. 2 into 4, 8 minus 1 time, that is 7 times. Okay, so out of which I should split that into 2 parts. Left part will come in left half and right part will come in right half, something like this, right? So I need to consider the values of k which are 0, 1, 2 as well as 3. Now let me take the first value of k. N will remain 4, which is constant throughout the problem, and k will vary, right? K will take 4 values. They are 0, 1, 2, 3. Substitute the first value of k in this expression. You will get theta naught like this. That is theta naught is equal to 5 pi by 8, and s naught is given by e power j 5 pi by 8, and its value is minus 0.382 plus j 0.923. Next, similarly, find out the next value of theta, which is theta 1. That is when k is equal to 1, it is equal to 7 pi by 8, and s1 is equal to minus 0.9238 plus j 0.3826. Similarly, find out the remaining 2 poles. That is when k is equal to 2, you will get theta 2 is equal to 9 pi by 8, and s2 is equal to minus 0.9238 minus j 0.3826. Similarly, theta 3 is given by 11 pi by 8, and s3 is minus 0.3826 minus j 0.9238. Okay. So once you find out poles, what is the next step? The next step is to find transfer function. What is the formula for finding out transfer function? It is given by Hn of s is equal to 1 by summation left of poles s minus sk, and we have how many poles? 4 poles, and this can be expanded it like this. That is h4 of s is equal to 1 by s minus s naught, s minus s1, s minus s2 as well as s minus s3. Now substitute various values of poles, that is s0, s1, s2, s3. You will get back this and simplify this further. Again you can use the formula a plus b into a minus b, which will gives you a square minus b square. Now observe this. See, this and this are conjugate of one another. Similarly, first as well as last are conjugate of one another. So I can use a plus b into a minus b, or now since we already studied this and we have wrote it as a table, from the table also you can, now if you can remember, you can write it this directly. This is direct answer which I have written here. Or if you don't want to remember, you can simplify it like this, just like how I told, that is a plus b into a minus b formula, so that you will get this. So what is this? This is normalized low pass filter answer only, is it not? For order n is equal to 4. But what I need to design, I need to design high pass filter. That means I should use suitable transformation to convert normalized low pass filter into high pass filter. So in general, I need to know the answer for cutoff frequency. In general, I know the formula for cutoff frequency is omega c is equal to omega p divided by 10 power minus kp by 10 minus 1 whole power 1 by 2n. And if you substitute that, you will get this, that is omega c is equal to 1.0693, because you know all these values, you can easily find out this answer. Now once you find out this answer, then by making use of suitable transformation, we will convert normalized low pass filter, which is represented by this transfer function, into a high pass filter transfer function. And transformation that is needed here is HA of S can be obtained by replacing S in H4 of S. This is H4 of S. This is H4 of S. That is, wherever you find S in H4 of S, replace S by omega u by omega c into S. What is omega u? Upper cutoff frequency. Have they given you the value of upper cutoff frequency? See here, omega u value. That is this value, right? Upper cutoff frequency, omega u divided by omega c into S. Omega u is 200, which was given, omega c, which we have found out just now, into S. So if you now further simplify, you will get S has to be replaced by 187.03 divided by S. What is the meaning of this? Wherever you will find S in H4 of S expression, which we obtained just now, there we should replace S by 187.03 by S, and it is like this. So substitute, simplify that further simplify, you will get back this, that is S4 divided by S square plus 143.13 S plus 34,980.22 into S square plus 345.55 S plus 34,980.22. Actually, we need to simplify this further, because I need Butterworth polynomial, which is of order 4 in this case. Even if you do it till here, it is sufficient. So if you want full marks, now if you have time in exam or in test, further simplify, or else even if you show up to here, it is okay. There is one question here, that is, now in the last class I have explained, if you want to convert normalized low pass filter into high pass filter, then what is the transformation I should use? I should use S, or S has to be replaced by omega u by S. Now did I use the same formula here? See here, there is slight change, right? Omega u by S, which I have written here, right? Omega u by S. But here I have included omega c as well. Why? What is the reason? The one which you are observing is analog to analog transformation, but it is not the same for Butterworth, right? For Butterworth, that is, if you want to convert normalized low pass into desired high pass using Butterworth technique, there is slight change in formula. That is, you need to include omega c. Okay, hope you have understood this particular problem. Thank you.